This clip is a lecture on Chapter 4, Analysis of Statically Determinate Beams and Frames. It is part of the theory of structure. This chapter we will learn about the beam and the frame under the action of the external forces, and the unknown of the beam and the frame are equal to the number of equation of equilibrium. So by doing that, this beam and frame is going to be the statically determinate structure. And the objective of learning is to understand and be able to determine the internal forces and bending moment occur at a given section of the given beams and frame. Like I said, after the action of the external forces, the frame and the beam are in equilibrium. And then when you cut a section of the beams or frames, that section will also be in equilibrium. How that section going to be in equilibrium? That section will be in equilibrium because the material of the structure have the strength to resist the external forces, and then it's develop the stresses. And if we count stresses, we will get the resultant forces and moment. And the second one, the student should understand and be able to draw the shear diagram and bending moment diagram of the beams and the frame by using the equations or by using the graphical method. We need to draw the diagrams because we need to find the maximum shear force and also the maximum bending moment in order to design the beams and the frame. So if we determine the shear force and the maximum moment incorrectly, our design result will also be incorrect. So this is very important thing. Okay, before we go further, let's us talking a little bit about the homework of chapter 4. In the homework, your student need to do the hand calculation and also needs to use the computer program to run the structure for the result. For example, for the problem 4-16 here, if we have the beam subjected to the force P like this, in this problem, the student must solve for the reaction and internal forces and bending moment in the function of the force P, the length L, and the position X. And then by using the computer, you guys supposed to assume something. For example, you assume P equal to 10 kilonewton, and assume L equal to 10. So that is going to be 2.5, 2.5, 2.5, and 2.5. You plug the P and the L into the equation of the shear force and the bending moment, and then you put the P of 10 kilonewton and the L of 2.5 kilonewton into the computer program. So the calculation from the program can compare with the hand calculation results. For the problem 4-18, this is much more simple. You just do the hand calculation and then you put the value into the beam's value into the computer program, and then you also get the result and then you compare them. By doing this, the result from hand calculation and the result from the computer program must be equal. If not, the hand calculation may be wrong, or the computer program input may be wrong, so the result wrong, or both of them are wrong. Okay, just check it out. The result must be equal. And the frame, next, the do that, just change, sorry on that. The frame, for the frame also, all the frame are going to be statically determined. That means it can be solved by using the free body diagram and the equation of equilibrium. Then you draw the shear diagram and moment diagram by your hand calculation. And then you input the configuration of the frame, the loading, the support into the computer program. Is going to produce the output for you. And then you compare the results. They must be equal. If not, there are some problem. Okay. Okay. We're gonna have 3 problem for the beam and 4 problem for the frame. This chapter will have 2 problems in the examination. One is for the shear diagram and moment diagram of the beam. Another one is the shear diagram and moment diagram of the frame. So this chapter going to have a lot of proportion compared to the previous chapters. Okay, before we go further, let us consider the real structure that we have. What we are have here is the precast concrete beam, reinforced concrete beam. The beam is tested by the full scale testing frame, and the beam lie along the horizontal and support by the pin roller. And since the hydraulic put the forces onto the beam 2 points and in equal magnitude, so we can determine the reaction on the beam easily. I like you guys to go to draw the model of this beam and try to draw the shear diagram and the moment diagram of the beam. And by the loading transfer by the P like this, the beam will deflect like this. And you may see the deflection are measured by using the LVDT, or the linear variable differential transducer over here. Also, the steel inside the beam attached by a number of strain gauges. These strain gauges link to the computer, so when the force act on the beam, they can study the behavior of the beam clearly. And by putting the force into the beam, the force also applied to the top, to the middle of the frame here. It's middle of the beam here. The beam attached to the column. This is going to be the orange column. So if the force act on the beam is P, the force will act on this yellow beam also P. And then the orange column gonna take the force of P divided by 2. Okay, and it transfer to the foundation of the frame. This is one kind of a full scale test. It's kind of very expensive. It also require a lot of planning. One of the requirements for planning is design the beam. When we design the beam, we also need to determine the maximum shear forces and the maximum bending moment. Okay, and you also need to estimate the capacity of the frame due to the applied forces here. Okay, that's show you the importance of drawing the shear diagram and the bending moment diagram. And I asked you for the giving load. Can you find the reactions and draw the shear diagram and bending moment diagram of the beams and also of the frame? Next, let us consider the, the bridge. This bridge have the substructure in the form of the cantilever frame. Okay, by the construction, the pie gonna be bored into the soil, and then they cast the concrete foundation, and they cast the column, and then they cast the crossbeam. The column and the crossbeam act together to act as a frame. Okay, and then during the construction of the substructure, they also cast this precast beam in the factory. This precast beam and the slab and the guardrail form the superstructure of the bridge to taking the load from the traffics. And then the precast beam will ship or transport to the 18-wheeler and coming to the site. When they arrive at the site, there are cranes that lift them up. After they lift them up, each of the beam will put in places, and then a precast slab put onto the top of the beam, and then some temperature wire and reinforcement also put into the surface of this bridge, and then the concrete pour out and makes leveling, and then we will have the superstructure to carry the traffic load. During the traffic load is a live load. The traffic load you can determine from the design manual of the Department of Transportation. Okay, and also the beam and the floor and the guardrail have their own weight. The weight of the beam and the live load gonna act on the beam as a uniformly distributed load, and then the addition of the beam will transfer to the 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 beam of this frame. Okay, and then all the force transfer to the foundation and the pies. This is another example of using the beam and the frame in our real life. Next is the steel frame. On this steel frame, during the construction, after building the foundation, the column were fabricated, and after fabricated the column, the girder will later put in places and then install in their position, and then the small beam will attach to the girder, and the joist also attached to the girder. By doing this, after finishing, the slab will put on the top of the joist and the beam, and the force, the loading from the slab will transfer to the beam and transfer to the girder. Also, the force from the slab will transfer to the joist and also transfer to the girder. All the weight that transfer to the girder will transfer to the column. And if you consider the connection of the beam and the frame over here is can be assumed as the rigid joint. However, the connection between the beam and the girder in this figure is not fixed. It is in the form of pin support. And the joints over here, if it have the slot along its length, this can move horizontally. This can be assumed as the lower support. So, in the considering of this steel building, we got to know how to build it, and then you will imagine how the force transfer from the slab to the small beam to the girder of the frame and to the column. Okay, and most of the time the support of the steel frame are fixed support, and it can take the load safely. Okay, that is kind of the introduction to the analysis of statically determinate beams and frames. And you can see that there are a lot of application of the beam and frame in our real life. It can be in the building, it can be in the bridge. Next, the 4.1. We are going to talking about the internal forces and bending moments at a given section. As I mentioned before, when the beam or frame subjected to the external forces, the support of the beam and the frame will have the reaction to make the beam and the frame in equilibrium. So, if we consider each part of the whole beam and the whole frame, that part of the beam of the frame also in equilibrium. How the section or part of the beam and the frame are in equilibrium? Because the beam or the frame may produce by a given material, for example, the steel. Okay, when the steel subjected to the force, the steel has the strength that resists the forces, and then the equilibrium produced. By cutting the beam or the frame at a given section, the internal forces and the bending moment also can be determined from the equation of equilibrium by using the state of equilibrium of that portion of the beam or the frame. By the definition, the internal forces and the bending moment are the resultant of the normal stress and transverse shear stress distribution on a given section of a structural member due to the external applied load. Like I said, they can be determined by the method of section. So, in short, the external load, for example, the load that's applied to this portion of the beam, will produce the stress. There are two types of stress. Actually, it's supposed to be three types of stresses on a section of a beam. Is the normal stress due to the axial load, the shear stress due to the shear force. That is normal stress due to the normal force, the shear stress due to the shear force, and the bending stress or fractional stress due to the bending moment. So, if you know the stress, actually the stress will produce the internal forces and the bending moment. Okay, the beam on the right subjected to the shear forces and have the shear stress transfer, shear stress distribution like this. We have this on chapter 7 of the mechanics of material. And the beam on the right or left is subjected to the bending moment, and it has the stress on the section in the form of fractional stress. This normal stress can be determined from the equation sigma equal to mc or y over I, and tau, the shear stress over here, can be determined from the equation VQ, the shear force V, Q, the moment of the area above the neutral axis, and divided by I. I is moment of the shear and the T is the thickness. Okay. At this point, we know that the external load will produce the stresses in the portion of the structure, and those stresses can be determined in the form of resultant forces and resultant moment. Okay, into dimension, the internal forces and the bending moment on a given section of a structural member are: first is the normal forces. Normal forces is the force that act normal or perpendicular to the section. Okay, the symbol is N. The second is the shear. The shear is the force that act parallel to the cut section, and then the symbol is the V. And the last one is the bending moment. Okay, that has the symbol of M. And each cut of the structural part has three unknown, and that three unknown is in accordance with the concept of equilibrium of rigid body. So we can use summation of x sub x equal to 0 to determine n. We can use summation of f sub y equal to 0 to determine shear, and the summation of moment equal to 0 to determine the bending moment. And the internal forces and bending moment for this section C. When you cut the beams will separate into two parts or two segments. And if we find the normal force, we find the shear force and bending moment at the section C on the left like this, by using the third law of Newton, we also know the normal force, know the shear, and know the moment on the right segment or the right portion of the same beam. And one more thing, we need to set up the sign convention for the normal force, for the shear force, and for the bending moment. And let us assume the tension is positive for the left portion, and the shear downward is positive. We use shear downward, and the moment counterclockwise. If we compute and then we get the negative value of n, so that n is going to be compression. And if we have the negative of v sub c, so the v is upward. And if we have the negative of m sub c, the moment going to be clockwise. Okay, that is the sign convention that we will use in this study. Okay, let's take a look at this beam. This beam have the pin A and the roller at C. Okay, and it's gonna have two reactions at A and one reaction at B. For the procedure to find the internal forces and moment at C, we first to draw the free body diagram of the whole beam. Okay, and for the free body diagram, the A is the pin. You got A sub x and A sub y. and B again is the roller, we got B sub y. By the action of the force F1 and the force F2, the force F2 is an inclined force. Okay, so this time we can determine the A sub x. If this is a theta, so this is going to be A sub x equal to minus F2 F2 cosine theta, something like that. Okay, and if you use the whole equation of equilibrium, you will get A sub x, A sub y, and B sub y. Most of the time we use the, the summation of moment first to take moment at the point of A to eliminate A sub x and A sub y out of equation, and then we can determine the B sub y. After you know B sub y, you use the summation F sub y เท่ากับ0 equal to 0. A sub y plus B sub y going to be the vertical force. After that, you cut the beam section at C perpendicularly to the axis of the beam, and then you may draw the free body diagram of that segment of the beam. Again, since this beam is in equilibrium, when you cut it, this portion of this segment of the beam will also in equilibrium. To be in equilibrium, this section must have normal force, must have shear force, and must have bending moment. Where these forces and bending moment come from? Come from the strength of this material, and then you can find the n sub c by summation of x sub x equal to 0. Okay, you can find v sub c by summation of f sub y equal to 0, and also you can find m sub c by summation of moment equal to 0. After applying the equation of equilibrium, you will find the normal force, shear force, and bending moment at C. Since this value of the normal force, shear force, and bending moment change with the location that you cut the beam, so the next step you're going to draw the shear diagram and moment diagram by cutting the beam with differences location, and then you get different value of shear forces with different location, and then you can plot the shear diagram, the bending moment diagram also. Okay, the sign convention. The sign convention, I should note that this sign convention is positive in our study here. So when you cut the section on the left, the downward shear is going to be positive, and the counterclockwise moment is positive. And then you may see the positive moment produce the compression on the top and produce the tension on the bottom, as we know before. Okay, let's take a look at an example. Now we have the beam. Okay, this beam is beam ADB, and this beam subjected to the 500 Newton per meter, and this beam support by the pin at A. So over here gonna have A sub x and A sub y, and at the B there is a member pin on the top and pin on the bottom, I mean pin at C and pin at B, and there is no forces between B and C. Do you recall what we call this member BC? If you can remember, this is the two force member, and the two force member will have the forces along its axis. Okay, it can be in tension or it can be in compression. Okay, by doing that, we can conclude under the action of 5 Newton per meter loading here, we're going to have the reaction A sub x and A sub y, and also the force along the line BC. Okay, if we understand that, we can draw the free body diagram of the beam correctly, taking the beam out of the support under action of the no forces. You may set the reference y and x axis here, and then the A sub x and A sub y. A sub x going to be in x direction, A sub y going to be in y direction for the reference axis, and the force in BC along its axis. So the angle here going to be 45 degrees. And by using the equation of equilibrium, you can find the reaction. The best way is taking the moment at the A to be 0 to eliminate the A sub x and A sub y out of the equation. And then the F sub BC, if you cosine it, it's going to be the horizontal force and point to A, produce no moment. So only the F sub BC sine 45 degree gonna produce the moment. And F sub BC sine 45 degree gonna rotate what? Gonna rotate counterclockwise. See my arrow, see my arrow. Counterclockwise about point A. And F sub BC sine 45 degree gonna time the moment arm. The moment arm is what? Is 2 meters. So the first part we have the F sub BC sine, and then time moment arm of 2 is positive because it's counterclockwise. And then the uniformly distributed load here, okay, is gonna rotate clockwise. The resultant of this uniformly distributed loads gonna be what? Gonna be the 500 Newton per meter times the whole length of the beam. So that is gonna be 500 times 3. And the point of action is going to be the centroid, of the square area. So the length here, since all of them are 3, so it's gonna act at 1.5. And since this one is 0.5, so the length between the line of action of this resultant force to point A is going to be 1 meter. And then it's rotated clockwise, so it's going to be negative, right? It's going to be negative. And then it's negative 500 times 3, and over here is only 1 meter. It's 1.5 minus 0.5. And put it into your calculator. The F sub BC is going to be 1060.7 Newton. And then summation of x sub x equal to 0. So you get A sub x. The A sub x going to be what? A sub x is positive to the right. So this one is F sub BC cosine 45 degree is going to put on the left. So it's negative. So you get A sub x of 350 Newton. And the last one, summation of F sub y equal to 0. This time we are going to have A sub y. Up is positive. And this one is F sub BC sine 45 degree. These two terms are plus. And then the 1500 Newton here going to be minus. And then you get the A sub y of 750 Newton. That's the reaction. To determine the internal forces and bending moment at D, we got to cut the beam at this D section. Okay, cut the beam at D. When you cut the beam at D, the beam will subjected to uniformly distributed load of 500 Newton meter, and also the reaction 750 Newton A sub x and 750 Newton A sub y. By doing that, at the cut section need to have the normal force, shear force, and bending moment to take the portion of this beam in equilibrium. Being in equilibrium, your summation of x sub x equal to 0. Okay, n sub d is plus, and 200 also plus. So n sub d actually have the opposite direction as you assume here. So n sub d is compression. Then if you take summation of f sub y equal to 0, okay, this v sub d is downward, is negative. The resultant force, when you cut this portion, the length of the beam is 1 meter. So the resultant is 500 times 1, and then downward, negative. And the resultant A sub y upward is positive. So we got V sub d of 250 Newton. That means this is the correct, okay, the downward is the correct direction of V sub d. And the last one, you take moment at D over here. When you take moment at D, the counterclockwise M sub D is positive. And then you can see the 500 times 1 gonna time moment arm of 0.5 is also rotate with M sub D is positive. Okay, this one produce no moment because it's point to point D. Another one is 750 is opposite to M sub D, so it's minus 750 times 0.5, and then you get M sub D of 125 Newton meter. At this point, you may recall from the mechanics of material. You may use the knowledge from chapter 1 of mechanics of material to find the normal stress due to the normal force. Okay, this will determine by sigma equal to n sub d divided by a. This shear force will produce the transverse shear stress. If you may recall, the tau over here will be equal to V sub d times Q is moment of the area about neutral axis, divided I is the moment of inertia, and divided by T. And the moment M sub d gonna produce the fractional stress. This can be computed by sigma equal to M sub d and time y. Y is the distance that's measured from the neutral axis up to the point that you are interested, and divided by moment of inertia I. And then if you go further, you also be able to draw the normal stress distribution on this section, and also the transverse shear stress distribution on this section. But if you cannot remember at all, that means it's time to go back and take a look what you have in the mechanics of material. Okay, and we should finish this clip at this point. The next clip we will talking about the shear and bending moment diagram of the beam.